Hi students, in this video we'll be doing another interesting lesson on triangles. Well, I hope you've all seen video 1 where we learned about the difference between similarity and congruency. In this video we'll be looking at specific conditions required for similarity in triangles, and we'll also be looking at this really exciting theorem called basic proportionality theorem. How do we prove this theorem and what is its converse? Later, we'll also be looking at what is the importance of learning all this in mathematics. So this is a very exciting video. I hope you all have your superpowers right with you so that we can get started. Okay, super cool revision. Okay, if you already know the answers to all these questions, go ahead to the next part of this video. Otherwise, let's do this exercise together. First, let's recall what is similarity and what is congruency. Similarity means what? That in two figures, two conditions should be exactly satisfied. That is, their angles should be equal and their sides should be proportional. Okay, so what does this mean with an example? Let's take an example. They're asking you, all triangles are similar as long as they are what? Isosceles or equilateral? Let's find similarities meaning with this example. Isosceles triangles satisfy what condition? Do you remember what isosceles triangles are? Isosceles triangles have two equal sides. Therefore, they have two equal angles. Okay, those angles could be of any size. Okay, so for example, this isosceles triangle right here could have two angles of 60 degrees each. While this little isosceles triangle here, if I draw it a little bit differently, it could have two angles of another size like 30 degrees each. Okay, so these two isosceles triangle, if you look at it, they don't have angles of exactly equal measurement. Therefore, they are not similar. So it is clear that all isosceles triangles are not necessarily similar. Okay, although they can be similar in some cases, they are not always similar. Now let's take the case of equilateral triangles. Equilateral triangles means what? All sides are equal, as it says in the name, and therefore all angles are equal. So if I have a big and then I have a small equilateral triangle, still in both of them all angles should be same size, that is 60 degrees always, and all sides should be equal to each other. So even this tiny one has sides of 2, 2, 2 length, and the big one has sides of 6, 6, 6 as length. Okay, when I simplify it, the proportion of the sides or the ratio of the sides in both these triangles, if I simplify it, it is 6 ones are 6 is to 6 ones are 6 is to 6 ones are 6. 1 is to 1 is to 1. The big one, and if I simplify this also, I get 2 ones are 2, 1s are 2, 1s are 2. 1 is to 1 is to 1 is the ratio in the small one as well. So the sides are all proportional to each other. In both the triangles, the sides are of the ratio 1 is to 1 is to 1. So all equilateral triangles are similar. They have exact same angles and exactly proportional sides. Okay. So we have revised what does similarity mean. So let's now recall what congruency means. Congruency means that two figures are exactly identical, which means they have the exact same angles and the exact same size, or the exact same length of sides. Two figures are congruent if and only if you can literally place them on top of each other and they will match in size as well as in shape. Okay, so let's look at the first question. All circles are congruent or similar? I have drawn two circles which are exactly identical. Probably if I put this circle on top of this one, they will exactly match in size as well as in shape. Now what if I draw a really tiny circle? Then are these two circles congruent? No, not necessarily. So this means that not any two circles are congruent. That means they may have different sizes. However, if you see, all circles are similar. Why is that? They all have the same angles everywhere. In any circle, if I draw a perpendicular line to the center of the circle, I will find that the perpendicular line to the center of the circle is always 90 degrees. Okay, so this is true in any circle. Forgive my horrible drawing. I'm going to draw that again. Okay, so I'm just saying that any line drawn from the circumference of the circle is always perpendicular to the center of the circle, and this is true in any circle in the world. Therefore, the angles in any circle are same regardless of the size of the circle. So all circles are similar because they have proportional sides and they have the same exact angles. Okay. And why did I say proportional sides? Well, anytime you take the distance from the center of the circle to the circumference of the circle, the radius of the circle that is, it's always equal at all points in a circle. So that's why we say that the sides of the circle are all proportional to each other. So the circles are all similar. Now let's take squares. Squares have same exact angles, no doubt, 90 degrees. All angles are 90 degrees in all squares. So all angles are equal in all squares. Are all the sides proportional? Think about it. Just like in the case of equilateral triangle, you can find the answer for squares also. If you take any two squares, since their angles are all equal and their sides are all of the same proportion, 1:1:1:1, you can say that they are all similar figures. The reason is, always the lengths are going to be equal to one another. So if you simplify the ratio of these lengths, you'll always get the same ratio, 1:1:1:1. And the angles are always equal. So they are similar. The next one. Two polygons of the same number of sides are similar if, what are the options and to which of A and B do they belong? This is the question. Polygons means what? Polygon is any figure which has many sides. So now let me take any figure, for example, a figure which has 5 sides. 1, 2, 3, 4, 5. Now let me take a little figure with 5 sides. What do I call this? I call this polygon a pentagon, right? 5 sides. Okay. Now, they are similar if their corresponding angles are equal. That's true in any figure, okay? So this is the answer for A, equal. And their corresponding sides are proportional. This is what I've written here, right? This is the condition for similarity. So that's the answer. B goes to B and A goes to A, okay? Last question. We are almost there, guys. Good job. A lot of energy you have. Let's do this. Given two different examples of a pair of similar figures and non-similar figures. So let's give two examples of a pair of similar figures. We just discussed what are two similar figures. Any two circles, any two squares, any two equilateral triangles. Not just any two triangles, but any two equilateral triangles, right? These are all similar figures, okay? Non-similar figures. If I take one isosceles triangle, which has only two equal angles and two equal sides, and I take one equilateral triangle, which has all three equal angles and all three equal sides, these two are non-similar figures. Can you tell me why? Think about it. The reason is, in an equilateral triangle with only two equal angles, it has to be the case that one of the angles is different from 60 degrees. Let me be clear. So let's take this isosceles triangle to have one angle 30 degrees equal to the next angle 30 degrees. You know that all three angles in any triangle add up to 180 degrees total. That is the angle sum property of the triangle, right? So the third angle has to be 180 minus 30 minus 30. It has to be 120 degrees. Okay. So this is the measurement of the angles of the isosceles triangle. Now let's look at the dark green equilateral triangle. Here all three angles are equal. So if I divide 180 degree by 3, I get 60 degree each. That is the angle size of the equilateral triangle angles. So it is clear that the angles are not equal in both these figures. Since the angles are not equal, condition number 1 is violated and these two figures A and B are dissimilar or non-similar figures. Okay. So you can come up with thousands of examples like this on your own because your brain is so powerful, and understanding these fundamental concepts gives you the superpower to be able to crack all the triangle shapes in the world, including the ones you see around you in nature. So we just talked about this similarity of triangles is super easy. It just needs two conditions. One is that the angles should be exactly the same in both triangles and the sides should be proportional. So the angle should be equal and sides should be proportional. If there was even one condition that is not being met, the triangles cannot be similar. So if you take two triangles of these two shapes, then clearly you can see that the angle of this triangle there is one angle that's 90 degree. In this triangle probably no angle is 90 degrees, so the angles don't match, so they are not similar triangles, right? So there can be cases where the angles do match but the triangles are not similar because the sides are in different proportions. That means that in this triangle the sides are such that these two sides are equal and this is different, but in this triangle all three sides are equal, so the proportionality is differing. So even if the angles were all equal, it doesn't matter, similarity is not satisfied. Only in occasional cases such as in equilateral triangles is similarity always satisfied. So in equilateral triangles, because all three angles are always equal to 60 degrees and all three sides are always proportional in the ratio 1:1:1, they are all always similar. So one thing we can say for sure is that all equilateral triangles are always similar. And the funny thing is that this Greek guy, this Greek philosopher Thales, he came up with this concept even before the similarity concept was introduced or thought about. He said that all equilateral triangles have sides that are proportional to one another and angles which are the same, and so all equilateral triangles are similar, and we call that the basic proportionality theorem. Now the basic proportionality theorem is one of the most important concepts when we look at triangles, and so we're going to delve deep into it and see what it's all about. So here we have four equilateral triangles all shown in green. They have different sizes but they have the same exact shapes, meaning they're all similar. So if I had to represent it, how would I represent it? I would represent it like this. This beautiful, tilde is the notation of similarity going forward. Just a little bit of a side note before we move into basic proportionality theorem in detail. Okay. So there are two equivalent statements of the basic proportionality theorem by Thales. The first one is the ratio of any two corresponding sides in two equilateral triangles is always the same. Equiangular means equilateral. It's the same exact thing in Old English. Okay. So the ratio of any two corresponding sides. What is corresponding sides? If I take these two sides, I have to take these two sides as well. Okay. If this is one side AB, the corresponding side in this triangle must be CD. You get it? So any two corresponding sides, if you take the ratio of their lengths, it's always going to be equal or same in an equilateral triangle or a triangle which has three equal angles. Okay, this is what he said. So he only knew that a triangle has three equal angles. He called that an equiangular triangle, but he said that if you take the ratio of any two corresponding sides such as the red side and the yellow side in both these triangles, the ratio of the sides length will be the same. Similarly, if you took the ratio of the red side and the red side in both the triangles, again you would find their ratios to be the same. Now we know that the ratio is 1:1. Right, because all three sides are in fact equal. At that time he did not know that all three sides were equal. He just knew all three angles were equal, and he said that any two corresponding sides should be of the same ratio. Now an equivalent statement which he said is very interesting. Let's read it out. If a line is drawn parallel to one side of the triangle, so say for example I take the side BC in this triangle. This is a side, and I draw a line parallel to one side of the triangle. So I draw a line parallel to BC. This is a line parallel to BC. Okay, meaning it has the same distance from BC forever and ever and ever. If I extend it on both sides, it will always have the same distance to BC. It will never come closer. It will never go farther. It is exactly parallel. Okay, so if I drew a line like this, and let me label this line for you. In order to make things easier for you, let me label this parallel line as EF. Okay. So if a line is drawn parallel to one side of a triangle to intersect the other two sides, so this line EF is intersecting the other two sides. It's intersecting AC and it's intersecting AB at two distinct points, right? Then what? Then the other two sides are divided in the same ratio. Wow, that was deep. So what is he saying? He's saying now that if I draw EF parallel to BC, which is a base of a triangle, I will see that the sides AC and the sides AB are divided by EF in the same ratio. So if I call this 1 and I call this 2, okay, this will also be divided in the ratio 1:2. Okay, if this was divided in the ratio 2:3, If AE by EC, the lengths were in the ratio 2:3, then so will be the ratio of the lengths AF by FB. If you're following what I'm saying in the figure, you will get it. Okay, so I'll repeat that once more. If I take any triangle, okay, and I take any side of the triangle and I draw a line parallel to that side, okay, then I will see that this parallel line is dividing the other two sides of the triangle in the same ratio. So this AQ by QC will be equal to BP by PC. Okay, so always this is the basic proportionality theorem in another way. Okay, so there were two things, in any two sides of an equilateral triangle will be of the same proportion, and the second one is the formulation of the basic proportionality theorem we just saw. This is marked as theorem 6.1 in the textbook, just FYI. Okay, this is the basic proportionality theorem proof, and I'm gonna make it very simple for you guys, so let's do it. Let's consider this triangle ABC, just like drawn in the textbook. ABC, okay, CPA. Then let me draw this side better. Okay, let me draw a line parallel to the base BC and label it DE. Now, basic proportionality theorem says that this line that is drawn parallel to the base of the triangle must divide the two sides of the triangle in the equal ratio. So it says that AD by DB should be equal to AE by EC. That's what we need to prove. We need to prove the basic proportionality theorem here. Got it? We need to prove that this DE is really dividing both the sides in the same proportion. Okay, to do this proof, let's do some simplification. So let's do some additional drawings here. Let's connect BE diagonal and let's connect the DC diagonal as well. Let's also draw a diagonal from D onto AE, which is perpendicular to AE, and similarly a line from E perpendicular to AD. Now let's go ahead and start the proof. Let's, for simplification, okay, I'm going to color this triangle DBE in blue. Okay, I'm going to color this other triangle DEC in green. Okay, that way you can easily figure out what I'm talking about each time. Okay, and then this ADE, right, this is a common triangle above. I'm going to make it yellow. Okay, so yellow triangle means ADE. Okay, this one. Okay, now let's start. First, let's take the area of ADE. You guys should come along with me. What is the area of a triangle formula? Area of ADE. It's half into base into height. Do you remember this? So, if I have to take the area of ADE, I can take it in two different ways. Right? If I consider AD to be the base, then I have to take the height as the perpendicular to AD. In this case, that is the line NE. Okay, this is one way of calculating the half into base into height formula for triangle ADE. Another way to do it is I can also take the other side AE as the base and the perpendicular from AE as the height, that is MD as the height. You get my point? Then in that case the formula will become half into AE into MD. Both of these are equivalent. Both of them give me the area of ADE. Noted? Okay. Now let's look at the rest of the things. Let's look at the areas of these two triangles below, the blue and the green one. If I have to take the area of the blue triangle, area of BDE, if I take B as the base, the color changed on its own. If I take BD as the base, then what happens is that the height becomes the perpendicular from BD. Now let's take this triangle, right, BDE. It's like this almost. You see, perpendicular for BD as the base would be a line drawn from E that is perpendicular to this line BD, right? And then you will realize that this perpendicular line in this case is the line NE, and it lies outside this actual blue triangle BDE. And so that is the height we have to consider when we take the area of this triangle. Similarly, if I have to take the area of this other triangle, the green one, the light green one, area of DEC, if I take EC to be the base, half into base into height, the height of this triangle is actually a line drawn from D that is perpendicular to this line EC on any side. Okay, so that is the line DM. It's perpendicular to the line EC. Again, it lies outside the actual green triangle. So that must be the area of DEC. Why am I taking all these areas? You might wonder. It's for a very good reason. Now we're going to start taking the ratios of each of these triangles to the yellow triangle. So we'll be taking the ratio of the blue triangle to the yellow triangle, which is the area of the inverse of that. So we'll be taking the ratio of the yellow triangle to the blue triangle. That is area of ADE by area of BDE. See, this is the yellow triangle. Let me actually color it in yellow. This is the yellow triangle. I'm taking the ratio of it with the blue triangle. Similarly, I'll be then taking the ratio of the yellow triangle with the green triangle for a very good reason. So when I take the area of the yellow triangle with the blue triangle, I want as many terms as possible to cancel out. Okay. The blue triangle's area, we have written here, this is the formula for it. It's half into BD into NE. This is what has been written here as well. In order for many terms to cancel out, it's better if I write the expression of the area of the the yellow triangle in a way that it has common terms with the area of the blue triangle. Okay, so for this I have chosen to use this as the formula rather than the second one. Okay, so half into AD into NE divided by half into BD into NE. Again, I can cancel this, I can cancel this. Hurrah! Maximum terms I cancel and I get this ratio. Similarly, when taking the ratio of the yellow triangle with the green triangle, I will choose the other formula for the area. I won't choose the first formula. I will choose the one with MD. Why? Because I want this MD to cancel out with this MD. Okay, and that's exactly what happens when I take the ratio. And I get AE by EC. Hurrah! That's equation number 2. Now, finally, we have these ratios 1 and 2. Why did we take them? Well, just look at these two triangles. Look at the blue triangle and look at the green triangle. They both have the same base. Which is the same base between the blue and the green triangle? Clearly, it is the base DE. It's a common base between both of them. If they have the same base and the same height, they should have the same area. Do you agree with this? If the blue and the green triangles have the same base DE, they have the same height, whichever it is, then they must have the same area because area is equal to half into base into height for both of them, correct? Yes. So, I know that the base is the common. I have to show that the height is also common. Is it really common or not? Let's think about it. DE is a line that is parallel to the base BC. Any two parallel lines have the same height throughout. Parallel lines never meet because the distances between them never ever change. They're always, for infinity on both sides, they're always equidistant, which means that any line, which means that the height, okay, of this must always be the same everywhere. And this line, which is the same everywhere, equidistant at all points, must be perpendicular to one of the parallel lines. So the height is this. You can draw a height like this. For this green triangle, you can draw a height like this for the blue triangle, and you will find that the heights are equal. Which means that the heights of these two triangles are equal and the base is common, which is DE, which means the blue and the green triangle have the same areas. If the blue and the green triangles have the same areas, it means that the left hand side of both of these equations is the same, because already the numerator is the same, ADE. Denominator, now we have proved that area of BDE is equal to area of DEC because they both have the same area, because they have the same base and height. Therefore, the left hand side of both of these is the same. If the left hand side of both of these is the same, then what does it mean? If the left hand side is equal to right hand side and left hand side is equal to right hand side and these two are same, it means these two should be the same, right? So then we have thus proved that AD by DB is equal to AE by EC. To truly understand this formula, I highly recommend that you try to write the proof on your own. It's actually quite challenging, but also it's very rewarding. Okay, you can do it. And if you have any questions or comments, just put it in the doubts in the comment section.